Hi, I'm Guang, 15 years old. In this lesson on the methods of limits calculation, we will be taking a look at this question here. Now, what is so special about this question? So we need to show that integrate from 0 to x cubed dx is equal to 1 over 4 x to the power of 4 by the limit definition of definite integrals. So first of all, we will have to take a look at what is the basic concepts of this question. Well, of course, integration, it is very simple to do if you already know or even learned a little bit of it, right? And then definite integration, you just have to, after integration, substitute the values inside, which in this case you have 0 and x, but you have to be aware, in this case, the two x's are different. Since you have an x within the integration, which is the variable, but the x on the boundary will be more of somewhat like a constant. Alright, so this is the kind of definite integration we are taking a look at in this lesson. But we need to show that this definite integration is true. So how are we going to do that? First of all, what is what is the integration exactly trying to find? So if you have learned about it before, integration is essentially finding the area under the graph, the area under the curve, whatever you have. Right, so that is what integration is trying to achieve. Then how are we going to find this area in a different way? Alright, so if you have learned about it before, this definition of definite integrals is actually what you might know as your Riemann sums, alright? But then again, what's so special about these Riemann sums? Now, in this case, there are, well, 3 different ways you can take a look at. So, if you have learned about Riemann sums before, then you probably will know about the left, the right, and a trapezium or trapezoidal, depending on where you are from. Since in the US it is a trapezoid, and in other places it'll probably be trapezium. Alright, so that is 3 cases where you can take a look at. But then again, how are you going to find all these area? So let's just take the most, or a pretty generic integration example, where you're integrating from a to b, and you have this specific function of x, and you have to integrate this. So how exactly are you going to find this area under the curve in a different way? So since I did say about the Riemann sums just now, but what is so special about this Riemann sum? Now this Riemann sum is essentially using areas of rectangles, adding them up one by one, extending from the point A to the point B. Alright, so that is what's so special about your Riemann sums. You're using rectangles to find the area. But of course, since it is a curve and not just a little square, this area would be slightly inaccurate, but beware, they're just slightly, since if you're using a bigger interval, of course, there will be more room for error. But if that interval you're using approaches to pretty much a line, well then in that case, your error, when you add all of them up, approaches to 0, which is why you can use your Riemann sums. Alright, so how are we going to represent it in words here? So first of all, we're going to start off with a limit. So why a limit, you might ask? Since you want it to be very accurate, which means you'll need to stack a lot of these lines or really thin rectangles together, it will essentially approach to an infinite number of them. So then you can have limits n approaches to infinity, for example. Now next, we need to represent all of these little rectangles, right? So once again, how are we going to achieve that? By making use of a sigma notation, now we just have to focus on each individual rectangle. So let's say we're using I. So I, let's say you start from 1 and ends at n. Okay? So I goes from 1 to n. Now, how are we going to find the areas of these specific rectangles? So of course, to find the area of a rectangle, you need a base times a height. But then once again, how are you going to find the area of each of them? So let's start off with the height. Now the height should be pretty simple since fx, the function of your specific curve, when you have f something, at that point, that point will essentially be the height at that point. So how are we going to represent it here? We are going to use xi. So we can have like from your very beginning x1, x2, x3, and so on until you reach point B, where it will be xn. Right, so this is your height of the rectangle. Next will be, of course, the base, the width. So this width, how are you going to determine it once again? So this width is actually determined by using your intervals that you have over here from A to B. So what amount of length is being spanned from A to B? Well, of course, that will be B minus A. So B minus A will be the entire length spanned throughout this region. And then how many pieces are we going to have within here? How many rectangles are we going to fit inside here? That's n number of rectangles, which means this will be divided by n. Alright, so this is what you get with your Riemann sums. Okay, so then of course you can make variations to it. This is the left variant since, or it can even be the right since it is not specific. But then, of course, there are many different ways to represent it. A left, a right, trapezium, middle point, whatever you like to make, alright? So, this is what you are going to see here. I'm just going to put all of these within, alright? So, this is essentially how we are going to show this definite integration is true. Now, we can take a look at how this graph will look like. So we are looking at a graph of y is equal to x cubed. So your x-axis, the y-axis, alright? Now you might be wondering a little bit, why are we just using the first quadrant, alright? Not even using the second, third, or fourth. So if you know the graph of y is equal to x cubed, it spans the first and third quadrants. However, if you look at the question carefully, you're given 0 to x. Now of course this is assuming that x is positive. If x is negative, then of course that'll be the other way around. But that, well, you just have to give it a negative sign to flip it back. Alright, so let's take a look at this. X cubed. The graph of x cubed is somewhat like the graph of x squared, but it rises much more quicker, while at the beginning, closer to the 0, it actually rises a lot slower. Alright? So this will be the graph of y is equal to x cubed. Alright, so you have this kind of a thing here. Now, since we need to integrate from 0 to x, assuming x is positive, that means it can be somewhere on like this side. So let's say this point here is an x. And of course, how are we going to separate this graph here again? Well, we're going to cut it into small little segments. Alright, so many of these pieces from 0 all the way to x, and that is how we're going to find the area under the curve. But alright, that means there's a little problem here. Since we are going to find the areas of this, the areas of these, and we're using rectangles, then of course you have to make a decision whether you want to use the left version, the right version, or a trapezoid. So what do I mean by each of these? Now, let's say you have these two lengths to choose from, right? These two heights to choose from. If you're choosing the left height, the area of the rectangle you're getting is essentially cut at this point. So then you're basically doing an underestimation of the area here. But let's say you're using the right height, which means the area of the rectangle will span all the way up here. And that means you're doing an overestimation. While if you're doing a trapezoid, then you're cutting across here, which is still a little bit of an overestimation. Alright, but of course it varies from graph to graph, so not necessarily always underestimation if you're taking the left and overestimation if you're taking the right. It varies. You need to check its concavity, alright? Concavity, increasing, decreasing, all that. Alright, so how are we going to deal with this problem exactly? Now let's say, since we have many of these little pieces, let's say we have an n segments. Alright? So we have an n number of these rectangles. Now, with the n number of these, we have to make a way to know how to pick each of them out, which is also somewhat like naming them, isn't it? So, how exactly are we going to use a specific notation in order to allow us to be clear of how to integrate this, or how to find the area of each of these rectangles? Alright, so of course there are a few different representations you can choose from, whether you want to use something like xi for this part over here, and then xi plus 1 for the other part. Well, once again, this kind of notation depends on you, since you can also change your variables like I, j, k, whatever you want. Alright? But this, you have to make up a way in order to be sure of how to determine it. So, one of the things here, what you need to determine the area of a rectangle, one is the height, the other is the base. So the base is basically delta x. And in this case of delta x, let's say you're using xi plus 1 and xi. So what does this mean for the base? And once again, you have to look at your number of segments. Since these are consecutive lengths along this x-axis, consecutive points along this x-axis, that means x is your total length divided by n. That would actually be your little interval, which is x over n. Alright? So this will be your delta x, which will be your base. But next problem, if you're going to use your sigma notation and you're just going to add xi, xi plus 1, xi plus 2, is there another better way in order to find out how to get these x's? So that way is xi. So how can you represent xi? In terms of x over n. So I'm giving you a little clue here. You have to represent it in terms of x over n. So how, you might ask? Well, once again, determine how many pieces are in front of it, behind it, whatever, alright? So xi, which means you have 1 until I, which is a total of I number of pieces, which will be this essentially, alright? So if you want to make it look better, you can either put it in front of x or behind x. So there, you have represented xi within a single fraction. But again, you have to be aware of your handwriting and various problems. since this I is no longer in the subscript. It is multiplied onto x over n. And originally it was part of the subscript representing each of these heights, alright? So, we have gotten two of these problems solved. How about we take a look at this example now. So, integrating from 0 to x cubed dx. So when you change this into your limit and sigma notation form, so limit n approaches to infinity, sigma notation I is equal to 1 until n. Now within here, what is your fx? So fx will now be your x cubed. So this x, you have to be aware that you have to kind of change it up a little bit. Now, what will be so special about this change here? So of course you could still use xi then cubed, or you could directly change it into xi over n cubed. Alright? So this is what we're going to have. Next, of course, is to multiply by your base, which is x over n, which is this part that we have determined. Or if you want to determine it another way, that is of course your x minus 0 divided by n. Right, so these are the terms we currently see. But is there any special things about it? Anything you want to take out? So when you're trying to solve a question about summation, you would want to be able to take out as many irrelevant things as possible. So let's take a look at this. What is the only relevant thing to the summation here? It is I, since everything else is multiplied on, which means we can bring everything else in front of this summation, where you're going to see x to the power of 4 divided by n to the power of 4, and sigma notation I from 1 to n, and this is I cubed. Right, so now this is just your simple arithmetic problems, which of course you do have to know the formulas for each of these. Where in this case you're going to have limit n approaches to infinity, x to the power of 4 divided by n to the power of 4, and your summation formula for something cubed will be, so in this case it is n times n plus 1 divided by 2, and this entire thing squared. Right, so that is the formula you will essentially have to solve at last. So once again, we can take out some irrelevant things like x to the power of 4 divided by 2 squared, which is 4, and then limit n approaches to infinity. So you do realize there's an n squared here, where you can immediately simplify with this. Then you have n plus 1 squared divided by n squared. Then you can use your conversion from infinity calculation to infinitesimal calculation to get 1 plus 1 over n squared divided by 1, which you substitute n in will of course give you 1. So your answer is 1 over 4 x to the power of 4. And this here is shown, right? So that is how you show that the integration of x cubed from 0 to x is 1 over 4 x to the power of 4 by the limit definition, alright? So you have to be aware of your Riemann sums. And of course, from person to person, there's different preferences, whether you like to use the left one, the right one, a trapezoid, that also depends on you. So, of course, when your teacher teaches you different things, you do have to know how to change from one form to another. But in this case, if you use either one of the three, or even 4, because some of you might consider midpoint another, but that's kind of a different formula. Alright, so, but actually for each of these different formulas, no matter how hard you try to get it, you always get the same final answer, alright? So, I hope for this lesson you're clear of it so far, and the main thing we've covered here is of course your definition, which is also your Riemann sums. The rest is just a little bit of knowing how to get your rectangles, your area of it, and of course the formula that you have to know at the back. Right, so I'll be ending this lesson here, and thank you for your watching.